the engineering of it as well, because you've got, you were talking about at one time, you've got, they would, go to a steel maker and get this, but
Yeah.
you end up with all this waste because you've got the steel, the same thickness,
Yeah.
the same width, everything all the way from top to bottom, which is actually making the building heavier, but unnecessarily so. So there's a lot that's evolved, right?
For sure. So I'll take your mind back to a very iconic picture, and the iconic picture is where in New York, I think it was New York or Chicago, they were building this skyscraper, right? And you see all these guys sitting out on a steel beam, right?
Yeah.
And and that beam was a traditional type of steel beam. I don't know what the depth was. It might have been a 24-inch, and it might have weighed 50 pounds per foot. That steel beam was designed back in who knows 1800s. You know, that configuration.
Yeah.
And in the engineering days, we had all the data for each and every type of beam that was manufactured out of the rolling mills. So you'd have this massive steel beam, and sometimes the loads on that steel beam are different at one point than another point.
Yeah.
So where you had a significant amount of shear, you needed lots of steel, and in the bending side, or when you're calculating bending moments, you needed more steel. But there's a piece in between that's neutral, right? And you don't need quite as much steel. Well, you were going to pay for that steel whether you needed it or not in the traditional building
Right.
methods. Then came along the pre-engineered building groups, the Butlers and the Varco Prudens, Robinson Building Systems, and they started designing using a more defined design system where they would actually calculate at each of the sections of the beam and the column what the moments were and what the reactions were. So then they started designing beams specifically to meet those, and then along comes computerization in about the 60s or 70s, and these building groups moved into the metal building system software. And so now you can literally design a beam that calculates what everything is almost every half inch or every couple centimeters of the beam, and it can tell you exactly how thick, how wide, how deep, all the characteristics. And so you're getting now building structures that are larger spans, but they're also lighter, and now it's more important to tie the building together with secondary structurals, right? Like wall girts and purlins and proper bracing in the right locations. And the building starts acting as a unified structure.
Right.
The one advantage of the fabric that we do, what we include is in our building design, we don't design the building to take in consideration any of the other materials for bracing. Like some buildings will take in consideration the metal sheeting on the outside, and they'll say, well, we got metal sheeting, so we can take some of that metal sheeting and use it as a diaphragm bracing so we can lighten up the cross bracing or the structure someplace. Well, if the metal sheeting comes off in a wind, all of a sudden you've got a building now that isn't quite as strong as it used to be.
Right.
Well, we consider our building, the structure, as a unified unit. So whether you have fabric on it or not, that building's going to stand there.
Oh, so even without the fabric, it is that.
That's
Oh,
right.
I see.
Yeah. So we put all of that energy into designing a building that's going to stand, whether it's got fabric on it or not.